Alright, that was kind of silly. That also means that for the first few minutes of today's lecture you won't have the voice recording. But it's not so much of a loss. Um, what we're going to do over here is we are going to calculate the surface normal, and for that um, we need to do the cross product. So if we have two vectors over here, we can find out the cross product and the surface normal as a product of that. It's just that we are not given the vectors. That's the only problem right now. So no one's giving me this vector A or this vector B. We're not given that. What we do have instead is the vertices. So if this is V1, if this is V2, if this is V3 and this is V4, we got all these vertices over here. And when we talk about these vertices, you know that you can select a vertex and you can actually read the coordinate from here. This is what we got. Is this thing clear? So the first question is, how do I find out vector A and how do I find out vector B? Vector B rather. So let me read these out and write them down somewhere so that I can use them later on. So this is vertex 1, this is 1, minus 1, and 1. Alright, so we got this first vertex. Right. So 1 minus 1 and 1, and over here for the second vertex we got 1, 1, 1. And for V3 we got 0, 1, and 1.55. 1.55 rather. And this one is 0, minus 1, and 1.552. Okay, so this is what we got. And let me just draw this part over here. We got a quadrilateral like this. Over here we got V1. Over here this is V2. This is V4. And this is V3. Okay. However, you'd notice is that we don't really need V3 because the vectors that we'd be working with, they're made out of vertex V1 and V2 and V1 and V4, right? So we want to form a vector over here. This is going to be our vector A, and over here we got vector B. That's going from V1 to V2, V1 to V4 rather. This is V1 to V2 is A. And we want to find out the surface normal in this form. Okay. So far this is what we got. Now, how do we find this out? How do we find out these vectors? So in order to do that, we need to use a little bit of coordinate geometry, or you can actually use vectors right here. They're closely related. Let me go to another page. It's easier done this way. Okay, we got a very simple setup over here. Let us take in 2 points. Say P1 and P2, and let me put that in a different place, maybe over here. Okay, so can we find the coordinates for P1 and P2 just by looking at this graph? Okay, you should be able to do that, and let me use 2 different colors. So for P1, we go 1, 2, 3, 4 units along the x-axis and 2 units along the y-axis. So the coordinate for P1 is going to be 4, 2, and the other one, since this is 4 already, 5, 6, 7, 5, 6 rather, 6, and how many do we cross it along the y-axis? 2, 3, 4, 5, 6, 7, and 8. So we got 6, 8. Okay. Now, if I wanted to draw vectors going from point O to point P1, or from point O to point P2, I can easily write them in component form, right? Vectors can be written with I, J, and K unit vectors. So you just give the coefficients. So a vector like OP1, if I want to treat this as a vector, we can write it as 4i plus 2j. And I should put hats over here because these are unit vectors. So this one again, OP2, if you wanted to write that, this is going to be 6i hat plus 8j hat. So easy stuff right there. Now what I'm more interested about is a vector that goes from P1 to P2. This is what I want to find out. So in this case, let's say this is going to be our vector V. Okay. This vector is the same as another vector. If I just copy this part, okay, it doesn't really matter whether I place this vector over here or I place this over here or if it's here, because vectors, they don't have origins, right? They can be placed anywhere. So I'm going to cheat a little bit right over here, and I'll say that why not place it right at the origin then? Why would I do that? Because if you place it right at the origin, then you can look at the tip of this vector, and then you can tell exactly what would be the coefficient for I hat and what would be the coefficient for j hat. Because if you look at this other vector OP1, you could read out this is 4i hat plus 2j hat, because that's the amount it cuts off from the x-axis and the y-axis. So if I place this vector, this new vector, from P1 to P2, and if I drag and put it on the origin, then this will tell me exactly what's going to be the coefficient for this part, this I hat, and j hat. Is this thing clear? No? I mean, let me know if this is not clear, I can go through this one more time. Not a big deal. What I'm trying to point over here, let me just make another copy. See, we got a vector OP1. Let me copy a bigger chunk. Right? OP1, we got this vector, and we can say that this vector OP1 is equal to 4i hat plus 2j hat. Okay? Because it takes away 4 units from the x-axis and 2 units from the y-axis if you place it right at the origin. Now, if this vector OP1 was not here, if it were placed in some other point over here, it would still be the same vector. Because by definition, vectors, they do not have any origin. Vectors can be placed anywhere. They have only two things. That's the magnitude and the direction. So the direction still remains, and the length of the vectors is still the same, so it doesn't really matter where you place it on your screen. Okay. So I'm going to use that to say that if I got this vector, I can actually place it over here for my convenience. It still remains the same vector. How is it a convenience for me? Because now I can see that for I hat, the coefficient is going to be 2, and for j hat, this is going to be 6. So this vector p1, p2 is 2i hat plus 6j hat. Is this thing clear? Okay. Now, how do we do this? See, this 4, 2 needs to be brought down to 0, 0. Okay? And in order to bring 4, 2 to 0, 0, you have to move this thing 4 units to the left on the x-axis. 1, 2, 3, 4. It has to come over here. Then you need to drag it down 1 and 2 units down the y-axis. Okay? So we had 4, 2 over here, and this is 0, 0. And in order to do that, you have to subtract 4 from 4 and 2 from 2. That makes it 0, 0. But the same thing needs to happen over here. 6 minus 4 and 8 minus 2. And that's exactly what it is. So, right over here, P1, P2, this new vector is going to be 6 minus 4 I hat plus 8 minus 2 j hat. And this we can easily see over here. This is 6 and this is 4, and this is 8 and this is 2. So what you're actually doing is you got 2 points and you're subtracting all the coordinates from the second point, right? You're subtracting P1 from P2 coordinate wise. 6 minus 4 and 8 minus 2. Is this thing clear? Now if I wanted to apply the same logic over here, we got V1, we got V2, and I want to draw a vector that goes from V1 to V2. How do I write that? If I want to write A is going to be V2 minus V1. So if you subtract one point from another point, you get a vector that goes from this point to that point. Okay? So the destination comes first, and then comes the source. Destination minus source gives you a vector from source to the destination. Okay. So what is it going to be like? V2 minus V1, we got 1 minus 1, this is 1 minus 1, that's 0. That's 0 I hat, plus 1 minus minus 1, k. 2j hat and 0k hat. Okay, so this is pretty much 2j hat. This vector A. Help me out with the second one, this B vector. V4 minus V1. This is going to be minus 1. 0 minus 1 minus 1I hat plus minus 1 minus minus 1. That's 0. 0j hat plus 1.552 minus 1. That's 0.552. K hat. Alright, so now we got two vectors, vector A and vector B. Okay. How do we do the cross product? In our previous class, when I asked about cross product, you guys are saying that in order to find the cross product, we do AB sine theta, which is partially right. I mean, it just gives you the magnitude of the cross product. It doesn't give you the direction. So if you need the entire cross product, you have to go in a slightly different route. We write it in the determinant format. Determinants, they look like matrices because it's organized in this fashion. And now we're going to write these two vectors. This vector is 0 to 0, and here we got minus 1, 0, and 0.552. Okay, so how do we carry out the determinant operation? Let me get a highlighter over here. Okay, so first of all, when we are trying to write this in a vector format, let me use a pen for now. So what we need to find out is the components for I, j, and k. I changed the color, and now I can't find the cursor. That's stupid. Okay. So I need to find out what's going to be the coefficient. This is going to be the n vector. Okay. I need to find out the coefficient, let's say k1 plus k2j hat plus k3 k hat. So k1, k2, and k3, these are three coefficients. All right. In order to find out the coefficient k1 for I hat, we have to freeze this column I. And then we multiply 2 with 0.55, and we subtract the multiplication of 0 and 0. We have done this before, right? So k1 over here is going to be how much? 2 into 0.552 minus 0 into 0, which is nothing but 0. Now this is going to be how much? 1.14 or something like that. 1.14. One zero, 1.104. Right, 10, not 1.14. My mistake. Okay, so now we can replace this k1 with 1.104. How about k2? Now this time around, Yeah, for both these things we got zeros. So K2 is going to be 0, and for K3 this time around we are going to freeze these. So 0 times 0 minus 1 times 2. So that's 2. K3 equal to 2. So let's just write down these two things. Now we got our answer that the surface normal on this surface is going to be how much? 1.104 I hat plus 2k hat. There is no j hat. Is this thing clear? So this is what we are going to do. That for any given surface, I mean this was still very regular, we made it out of a cube, but we can go for other weird objects. Let me just bring in the monkey. We got a monkey head, which is a polygon mesh, and it can look like a proper monkey if I use subdivision subsurface and increase this thing and also enable smooth shading. So now you see that it looks like a smooth object, but underneath it all, if you look at the real construction, this is nothing but a polygon mesh. This whole thing is made out of a lot of quadrilaterals, and in some cases triangles. So you got triangles over here. So in general, you got polygons making up this entire model. Okay. So if I wanted to talk about this particular surface, and let us enable these nice little normals. Now you can see the normals are going in all different directions. So how can we find out the surface normal over here? The trick is you need to find out the surface, the vector that goes from this point to this point. Let us call this vector A, and we need another vector that goes from this point to the other point, vector B. And once you have that, you can find out the surface normal with A cross B. Okay. The only thing that we need over here is the coordinate for vertex V1, vertex V2, and some of the vertex, let's say this is V4, if this is V3. So for any polygon, if I give you the coordinates for each of these vertices, you should be able to form these vectors, and then you can carry out the cross product to find out the surface normal. Is this thing clear? Okay. So based on our discussion on the OBJ files, we know that we have all the vertices, we know all the faces, so you should be able to find out each of these polygons, and then you can compute the surface normals. Okay. So that's what we do here. We find out the surface normals because it's really needed for calculating what's going to be the color for this vertex, for example, this one over here, and for everything in between. We can compute the color. If you look at this object over here, if I bring it out in the object mode, you see there is a color variation all over this little object. You see some parts are dark and some parts are shining bright. Okay. We can see the color variation if you keep on moving around. You see it this way, and this is really very important to have this color variation, because without that we wouldn't get any idea about what this object is going to look like. Okay. Let me just render this out for you. If I painted it in total darkness like this, in black. We only see a silhouette. We don't get the details. We don't understand that there are eyes over here, there's a nose over here. You see nothing because there is no color variation. It's painted in a single color, just black and nothing else. But if you paint it in gray, different shades of gray, without even introducing red, green and blue, you can still understand every little detail of this object, because some parts are in shadow, some parts are in light, and it gives you the sense of depth in all these places. Okay, so this shading that we have on this object is very important for us to understand the structure of the object. Okay. And for that we need to compute exactly what shade to put in. We can't do that without using surface normals, because in our last class I showed you that in physics we learned the law of reflection, that light comes from any light source. It can even be the light from the projector. It comes over here, bounces off on this surface and goes back to your eyes. That's why you see that there is a board right there. Otherwise you won't be able to see the board. Okay. So one way or another, I mean, we're computing the surface normal without knowing that. That's in real life. But if it comes to computer graphics over here, we have to do the computation by ourselves, because we have to produce that picture. Okay. So with that said, I want you to realize one really important thing. Computer graphics in many parts is mostly about faking. See, we got few faces over here. There are not many faces, right? Here we got a face, here we have another face. Okay. But it looks like a smooth object. However, if I go for the default setup, which is the flat shading, you can actually see the polygons that made this object. We see each and every polygon over here, right? So all these polygons, they made up this object, and we can see them. However, if I go for smooth shading, we don't see that. Flat shading and smooth shading, there is a big difference. Okay. I want you guys to look at one very important statistics that Blender shows you right here, right up on the top. Okay. So you see it says Blender render, that's the render engine that's being used. It gives us the version number, and then the important statistics. It tells us how many vertices are there in this object. 7,958. How many faces are there? 7,872. And the next information is the most critical one, the number of triangles. All these faces, they can be made out of quadrilateral. They can be made out of triangles, pentagons, heptagons, or any n-gons. So what we have are polygons, but when you take any quadrilateral, we got a quadrilateral over here, we can always break it into two triangles. Okay. Any polygon can be broken into triangles. That's the basic building block of all these 3D models. Okay. This is known as tessellation, that you can break something up. Like if I take this paper, it's a really simple task. If I take this paper, it's a quadrilateral. It has 4 different sides. I can break it apart into a triangle like this. Right? If I bring in a diagonal, I will have 2 separate triangles, one over here and the other one over here. It doesn't change the geometry. It is still a paper, one single piece of paper, but I can have 2 triangles that make up this quadrilateral. And similarly, if I have a polygon that has more number of sides, I can still break that apart into triangles. So what I want you to realize over here, that if I go into the edit mode, see the number of edges, faces, and vertices Oh, I have a subdivision subsurface. Let me disable that for now. Let me get rid of that. So right now what we have, if you look at this monkey, we have a very faceted render right here that all these polygons, they're quite visible. Right? Let me come out of the zoom for a bit. So right now we can see all these faces because I didn't try to smooth it out introducing new vertices. And I can still go for the smooth shading, which is not as good as before, like with the smoother version, but it is still much smoother than what it was before. See, if you try to compare this with the flat shaded version, there is a clear distinction. Is this thing clear? Okay. So if you look at the geometry, exactly how this is composed. So how many faces we got? 500. And how many triangles? 968. So if I just click on the smooth shading, now it's smoother. Do we have any change? The number of vertices, the number of faces, the number of triangles, they're still the same. Okay. Let me go for a better example with another object. So I'll go to another layer and insert a, let's say, a cylinder. So in this cylinder we got this faceted view. We can see all these faces. We see this face over here, we see this face over here. Now all these faces are very much visible. If you look at the number of vertices and triangles, we see we got 34 faces, we got 124 triangles. But if I go for the smooth version, it looks really smooth, right? The cylinder looks really smooth. Did I increase the number of triangles, number of vertices? Nothing. They remain the same. See? Looks like a nice cylinder over here when we go for the smooth version, but not so much when we go for the flat version. So what is it that really happens over here? Why do we see this with faces, and when we click on smooth, we don't see them anymore? Because we're not changing the geometry, then something else must be happening. Okay. What I mean by that is, if you, let me just delete this cylinder, and I have shown you before that if you get a cylinder with fewer vertices, then it doesn't really look like a cylinder at some point. Okay, this is not circular anymore. You can clearly see the polygon. But if you keep on increasing the geometry, I mean by default we had 32, and if I increase this to, let's say, 300, now this becomes really smooth, right? So one way to make things smoother or carry out a lot of detail is by increasing the geometry. If you increase the number of polygons, yes, definitely you're going to get better results. No question asked. Okay. But that comes with a price. That needs a very good graphics card and a very good system to run. So the games that we played like 15 years back, they didn't have that much good graphics. You could see like boxes, the characters were not that realistic, but if you play a game from 2017 or 2018, they're very much realistic. Okay. So the models, they come with a lot of details, but they also need a lot of processing power. And you can see that like if you played car racing game like NFS, if you see the evolution of it, how the game evolved, what the cars looked like back in 2000, for example, compared to what they look like now, there is a big difference. It's not because our artists were not that great before. I mean, we have the same people, we're drawing the same thing. It's just that we didn't have enough processing power to render them in a real-time fashion. So as time goes on, we're coming up with a better graphics card, better system, so we can throw models with higher details at them. Okay. However, just because you can do that, it's not a good idea to increase the geometry because it slows down the entire process. So if you can do it in a cheaper way, why not do that? So right now, this is a cylinder with 300 vertices. If I drop it down to 32, it doesn't look good. But if I turn it on the smooth shading, okay, it becomes smoother. Maybe it's not as good as the previous one, but the number of triangles really makes a big difference. Okay, so that's the point I want you guys to understand, that how can we fake this without actually increasing the geometry of it. So what happens over here, let me enable the surface normals. See, for each of these surfaces, we see the surface normals, they're sticking out and they're going all in their separate directions. So what happens over here, if you look at two rectangles, I got one rectangle over here, another rectangle over here, they tell us that the surface normals are rightly going this way and that way, which is fine, right? However, if you look at the common point over here, it has two things. For this face, it's saying that the surface normal goes in this direction, and for the next face, it's saying that the surface normal needs to go in a different direction. Okay, that's why when you render this out, you see a clear line between these two faces, because it has two different responses for the surface normal. It gets rendered in two different ways. And that's quite evident if you go for the flat shading. See right here, we get two different shades of gray for two different surfaces, because right in the middle there is a difference, and that's because the surface normals, they don't agree with each other. Okay. The easiest way to fake this without increasing the geometry is why use two different surface normals like this. We will compute the surface normals, and then for the common vertices, we will use an average of these two. And again, an average over here, after computing all the surface normals, if we compute the average, then it will make it smoother. That's exactly what happens. Okay. So if we go over here, when you turn on the smooth shading, it's not really increasing the geometry. What's happening over here, that if you look at this particular vertex, we have four different surface normals, right? So this guy right here will get very confused which one to use. So we are going to use an average of all four of these surface normals. And that's how we're going to smooth it out. Okay, without increasing any such thing. For some of these objects, smooth shading is great. For some of these things, smooth shading is not so great. Let me show you that example also. Okay, so let us put a cube in here, and right now we have flat shading on. Okay, if you turn it to be smooth, then it looks a little bit weird. You don't want that, right? It needs to look like a cube, and we see artifacts over here like a diagonal, a bright diagonal over here, a bright diagonal over here. It doesn't really look good. Okay. So for flat shaded objects, for very hard edges, you really want to leave them as flat. Okay. But if it's a curved surface, then in most cases you want them to be smooth shaded. Okay. Let me show you one little thing that we have over here. When we export this to Wavefront OBJ, we have done that before. Let me put it on the cube over here. When we export this, where's this desktop? Okay, I've just exported this. Oh, I got too many objects, but I can read the cube still. Okay. That line right there is off. That means smoothing is turned off. Okay. So if you have smooth faces, then S will be turned on. Otherwise, it's going to be turned off. This is how you tell whatever software is rendering out this particular model. This is a 3D model, right? We got a set of vertices, we got a set of faces, everything is defined over here. We can render this out, but we need to know which faces are smooth and which faces are not. Just by looking at this flag, it can be turned on or turned off, and then we render all the faces that are following that point. We can render them either as smooth or as flat. For smooth, we need to do something a little bit extra. We need to calculate the normals. Per vertex normals. We are calculating per surface normals right now. For each surface or each face, we calculate one normal, but then we have to calculate per vertex normal. Okay. So here is this feature that I was unchecking. File, export, wavefront OBJ. And let me just zoom it up and show you guys over here. See, there's this option that says write normals. So if you enable that, that will write the vertex normal for each of these vertices. If I enable write normals, let me just do that. And I'm going to export this object. So that will change a few things. Let me show you what happened. Oh, sorry. I generated this thing, and this brings in VN lines. These are the vertex normals. So for each vertex, we had 8 different vertices. We now have 8 different VNs, vertex normals, and that will tell us what's going to be the normal for each of these vertices. It also changes the face lines. How so? We now have 1 and then 2 slashes and then 1. So when we are rendering this face, the first number over here tells us which vertex to use, and the second number over here tells us which vertex normal to use. Okay, so these are different vertex normals, and they're put over here. Since this is a simple object, that's why you see 1 and 1, 2 and 1, 4 and 1, and 3 and 1. But things can be different. You can use different normals depending on how the object looks like. Okay, so you can see that we have 6 different normals that are being used, right? 1, 2, 3, 4, 5, 6, and this is how it goes. These are the vertex normals. Any question about any of these things? Yep. All right, so we will have similar tasks in our midterm exam, where I will give you a model. I will ask you to compute the surface normal of a particular face. I will identify that, and I'll give you the coordinates for some of the vertices. Okay. What you need to do there, you need to find out the vectors by subtracting one vertex from another, and then carry out the cross product. Okay. So this is more of a math exercise. You have done these things before in your physics course. Try to do some practice on how to do cross product on vectors, and this is not going to be much difficult then, because calculating the coordinates, or I mean, they may also be given to you. It's not going to be a big deal. All right, we got 2 classes back to back today, and I'm really sorry that again I'm late coming to class today. Again, the freaking jam at PM office. I will take a 5 minutes break, and then we'll start right away. We won't have a 10 minutes break here. We'll do a few things with Blender, because now we know how to edit objects. Okay. Previously we were joining cubes together to form, let's say, this podium or a desk like this. We had 2 different examples in 2 different classes. In today's class, we're going to work with a single cube, and we will make changes to that to come up with a solid object right from there, from one cube, not from many different cubes. Okay. So this is going to be more of a Blender class for the remaining part. And after the class is done, I'll give you 2 different tasks, one Blender assignment and one programming assignment. Okay, I'll talk about that when we come back. From next class, I'll be asking you to sign in a sheet where your names will be printed. It's just that, well, not from next class, after the add drop period is done, because now there will still be some changes, people adding and dropping sections, and then I will transfer all these attendance records onto that sheet. Which section is this one? Yeah, well, oh well, all right. Since you have already signed that, let's just use that for today. Please sign that then. I mean, sign for 2 different columns, one for the theory class, and again for the lab class that's coming up. If you have that lab. If you don't have the lab, then don't do that.